Should basic of math and calculus notes be on separate books? Yeah, this is a different lecture, different courses. Although I'm the same, I'm the one who are teaching both of the lectures, but that is different lecture. So my suggestion, you need to separate both. Okay, but you're going to see that some of the fundamentals you are going to need in calculus, they are being taught in basic of math. So you need to learn some of the basic of math if you haven't, and then maybe review, and then most of it will be important in calculus. Okay, so I will try my best um, to mix up this basic of math and calculus, so you know which part that are really being emphasized and needed to calculus. Uh, Helen, I would like to know when you are going to arrive. Do you have any estimations, maybe schedule? Will it be like October, 24 September? Okay, that's still okay. I can offer hybrid classes. So we are going to have offline and online at the same time. So you can just go to the classroom for the others. We can have um, classes as usual, but I will open these WebEx for the abroad students who are not yet be able to come. Okay, so I think that will be our solutions for those of you who are not be able to come. Okay, okay, and please let me know whenever you are like. I think some of the students still like outside of Taiwan. Scarlett, will not affect our assistant. What do you mean by assistance? I think uh, it's still okay. I think it's still okay. Do you mean the teaching assistant, the TA, or oh yeah, yeah. I will try to discuss with them what they should do, but I hope they can give you probably maybe additional homework to be added for the missing classes, or something that can be substituted because of the missing classes for the teaching assistant. But I will discuss with them first, okay? And we'll let you know soon. Okay. Okay, I think we can start our class. Let me share my screen. Okay. All right. Let me check if my pencils already is charged. Okay, it's already 80%. Okay, I think I can start now. Let me change first my settings. Okay, so basically, what we are going to do for today's class is just take a small review, and we are going to start with function. And we are going to start with function, the most one of the most fundamental concept in calculus, okay? Or maybe in in basic science. Okay, so first, if you think about calculus, if you look for a definition, there will be some words, some meaningful words behind what is calculus. But what I want to write here is, if we look on the history, calculus is basically it's based on the literal meanings is marbles, marbles, like the circle, like marbles. And back in time, people usually use this to count, for counting. So basically, it's for counting, and the modern science defined calculus as um, a fundamental science for everything that has change. Okay, so this will relate to change. Okay, and from this aspect, and from some invention, uh, from history, we learned that uh, something that related to change in most cases will be divided by two. We call the principle for derivatives and integrals. And this is basically what calculus is. So first, something that derived and something that integrated. And both of them are describing how something is going to be changed. Okay, but we will talk about this in later sections. But to make it go through to this derivative integration, first we need to define what is functions and why it's so important for us to understand. Okay, so let's look on this words functions. So what is functions? So what is functions? If you think uh, like a machine, it functions like a machine. Let's say we are going to have, or maybe let me just draw quickly. Let's say f like that. Okay? Let's imagine this as a machine. Okay, so what function really means is whatever we are going to put in, we call this as some input. We are going to have some results. Okay, we are going to have some results. So imagine like maybe in the manufacturer, you put some ingredients and you get the final results, your product, right? Or maybe you can imagine also, like, if you cook something, you put some ingredients and the result is your, like, maybe you cook like noodles, so that's your final product, right? It's very different from the ingredient. Okay, that's the thing. So this is coming out as the output. And to describe what this input is, because it can be anything, and something that can be anything, usually in math we call with the symbols or variable x. Okay, and because we put into this machine, then our output is, we call f of x. Okay, so I think that's very basic, and I think some of you already know, then practically using this for many times, right? For years, like in the from I think from elementary, junior high, and high school, you are really frequently using this notions, this f of x, right? Okay. We can also imagine that, maybe let me put this around here. Okay. So if we think these two as our, let's say it's like our base, okay, our base. So this is, let's say, D, and this is E. Let's say this is E. Now if we have the input, let's say this is the X, okay, And we are going to put x with some arrow, and we can imagine this arrow as our f or functions, okay, our machine. The results will give you f of x, right? In the same way, if we have, let's say, another variable, let's say a, we put through the f, and we are going to get f of a. So everything from this d we can pinpoint and then making into the e. Okay. Now I will write the um, the official definitions for functions. Okay. But this is how you can visualize functions. Okay. Okay. So function, we can say function is something that it's kind of a rule. Okay. So function, or maybe function f, is a rule because we define f from previous page. So it's a rule that assigns uh, each element x in D, their home, basically exactly one element called f of x in set E. Okay. And D and E, we consider both are a real number. Okay? I hope you get the idea of real numbers within this calculus class. If not, then we will know if you've taken basic of math, you can also review that as well. Okay. And then the set B, we call this domain. The domain of the function. Domain of the function. We will talk about this a little bit later on. So if we talk about domain, we are going to talk about the range. I need to write with red, so you need to see that this is complete each other. So range is possible value or set of possible value of f of x as x varies through domain. Okay. We can also see this domain in range if we draw some graph here. Let me draw just a random functions. Let's say this is a function y equal f of x. Okay, now we are going to see that from this picture, from this figure, uh, every x from this point here, they will assign each point from x, and then that they get each point in this function. Okay. So by this picture, we could say that this is our domain, because this is the set of possible x that can be assigned to the functions. Okay. So we say that this is domain. And the range, okay, the range will be from this. Remember, from the definitions, range is the possible values of f of x. So we could see from the domain what f of x that can be determined. So of course, it starts from this, from here up until here, to high. Let's go here, right? So this will be our range. Let me write here range. Let me make it clear. Range, okay? Maybe make it like that. Make a dash. Okay. Okay, I hope this is very clear. Domain and range, okay? Well, maybe later we can have some set of exercise, or maybe I can review tomorrow in the tomorrow's class. Okay. Okay. Now, to give you more idea of a function, as I mentioned in Monday's class, in the morning class, that supposed to be the TA class, the function can be represented as several ways, in the several ways. So we can represent as words, we can represent with graphs, we can represent with table. Well, probably when you read the question, some of you maybe not really agree with me, but this is what function is, okay? And some with the formula or algebra. So let me just copy something from the textbook. Maybe I will write around here. Okay. Now to give you just some knowledge, let's just read this. Okay. So we are given a description of a function in words. Okay. So P is the human population at the world time T. Measure T so that T equals 0 correspond to the year 1900. Table 2, I will let you see the table 2 later. And then figure 9, blah, blah, blah. And then we have the formulations here. Formulations. So what's the function in words? The function in words described here. Okay. Or you can also write just this, the last part here, the algebra formula. Or if you would like to see the table, you can also make a table. So whenever you see a table, like for example x and f of x, you could say that that's a function, because every x assigned to some f of x, and then you can plot the points. Okay, that's the idea. Plot the point, and you see when you plot the points, and you can figure out, oh, this is some. I can figure some formula from it, like because today's we already have advanced knowledge how to do some interpolations, simulation, we can get the formula easily from software, right? But let's say we are going to see what it looks like. We plot the graph. And so we have this. But if you see, it's not really smooth, right? It's not really smooth. There are some. So if we connect each other, probably we need to find how to make the curve smooth and make the modelings or the formulations really represent the plot. Okay, that's the thing. So maybe we are needed uh, some modeling to fit the curve. We call it how to the fit curve. So maybe we get this red line. Okay, that's represent all the plots. So basically, that's in practice, okay, in the real life, that's how you are working with the functions. But for my class in calculus, we are going to simplify some things here, and then we are focused on the more fundamentals. Okay, so all the things is going to be a little bit abstract, but I hope that you can imagine that in some sense in the real life as well. Okay, so that's how to represent a function. So a words, a graph, a table, or just a formula. Okay, one of them is enough to represent as a function. Okay. Okay. Now the next sections, we're going to discuss again now what rules that will define functions. So how can we make sure that they're supposed to be function is a really a function. Okay. So that's how we are going to look at. Okay. Okay, I will move to the next page. Okay, if you want to see this for a while, please let me know. Okay, I will move to the next page. Okay, okay, now we are going to give you okay. Imagine that from the previous page, we did these things, right? Okay, okay, and we know that it's a function. But what's happened when we have, let's say, okay, can we do this? Can we do this? The second, so this is first one, the second one. Can we do this? Okay, good. Okay, this is okay. So when you vary your x, probably some of your x ends up with the same result function of x. Let's say this is a, b, c. Probably this a and b, it ends up with the same maybe one. Okay. It's okay. But if you have this, what do you think? This is A, B, 1, 2, 3. Okay, good. So I think in your intuitions, intuitively, you already know that we cannot do this because it's not make sense, right? We put some ingredients, but this ingredients becomes two results. It seems impossible. So if we try to make this visualization in the graph, okay, let me get through the graph. So if we have this, I think this is okay. This is okay graph, or maybe let me make a little bit random. This is okay because every x will be resulting in every different, right? It's different. I think that's okay. But when you have, for example, a graph that likes this, sorry, like that. This thing here is a trouble one. So let's say this is A. Okay, so we have this line here. This line is x equal A. Okay, so we have these 2 points that is crossing by this line. So we have, let me just write here. Let's say we have A, B, and maybe, or maybe C, and this is A, B. So from this one A, we get two results B and C, and it's not possible. And this line, this red line, is, I think, in our practice, in our practical use, this will be really useful. We call this the vertical line test. So whenever you have a functions, and you can see the visuals, the graphs, you can try to make vertical line. If your vertical line is crossing more than 1 point, which means that it's not a function. Okay, so vertical line, it's useful for determine to determine a function or to test a functions, testing a function. Or if you would like to write in more official words, a curve on xy plane is the graph of function, the graph of function of x if and only if no vertical line intersects the curve more than once. So the curve will be a function of x if no vertical intersects more than once. So if you see more than once, like the example, the left example here, then we say that it's not a function. Okay. So this is actually really good sampling for defining whether the graph or the curve is a function or not. Okay. Okay. Okay, I will move to next page. Now we can see some of our regular functions as you have learned before. Maybe just take the easy example to think. Uh, just the, let's say this is the x squared. Yeah, imagine this is our typical x squared, right? And of course, from the vertical line, nothing wrong with our function here. But how about if we have x equal y squared? So what happened here is we just rotate our curve, right? We rotate and we see that this will be around here. More or less, that is our function. It's probably here, okay? Now, when we draw this curve, this is just a curve, but when we draw the curve and we try to test whether this is a function or not, we see that it intersects more than one. So it's not a function. Yeah, 90-degree turn. Yeah, 90-degree turn. So this is not a function, right? Not a function. But we can make this a function if we can remove one side. So we can make it just this. And now we can have a function. Okay? Or we can have another way to think is just the bottom one. This is also a function. If you take the vertical line, then we can make functions from there. Another way to whenever you see some curve that it's not a function, you can think that if you can set some domain and maybe you can restrict some interval, maybe you can make a function. So that's also one way. Why the second graph? You mean this? Which second graph? Because we see that for, let's say this x is a, okay? When you put a, it gives you these two value, right? And that is when we call that it's not a function. Okay, when we talk back from the previous slides, where's my picture here? When we see here, it's the same conditions. We see that from 1x, it becomes 2f of x, two different of f of x. And that is not allowed in our definition of a function. What we are going to have is the first and the second one here, it's okay, because from 1x, we get f of x. And if we have, like for example, this one, we have a and b, they can be the same result. It's okay. Or this one is okay. But if we take from the same a, it becomes two different f of x, or two different results of a function. And that is, we define it's not a function. Okay. So if we take this into graph, this is what is visualized. Okay. And because we take this line here, we get the idea how to test whether the curve is a function or not. We say that it's called the vertical line test. Okay, I hope you get the idea. Okay, now we can set up a curve and make it a function. Okay, So let me take this example. Oh, I believe it will be the next one. Okay. Okay, after we know how to test the functions, the next sections, there are some functions that probably it has more than one equations, but it's still in on one same page functions. Okay, so we call that as a piecewise defined functions. Okay, so let's say we can write this as a piecewise defined functions. So in one functions, in one function, there will be different. There will be uh, different parts of formula for each domain. So what does it mean? It means that we can write functions something like this. For example, one part is 1 minus x for the domain that is x less equal negative 1. And then another part is x squared when the domain is x greater negative 1. And you can have several parts if you want and make like long piecewise. But this is just an example. Now, before we draw or sketch this piecewise, if we are asked to evaluate f at -2, okay. So since -2 is on the domain that is x less equal 1, okay, so we can say that this is x. So we can use this 1 minus 2, or we can say this is, okay. So we are not using the other formula. Okay. If we have f at -1, then -1 is going to be still in this part, still because it's less equal. So we are going to have 1 minus -1. Okay. If we would like to evaluate at x equals 0, 0 is on the right side, right? So 0 is here. So we can write that this is x greater than -1. So we could say that this will be 0 squared or 0. Okay. And now we can, because it's a simple curve, I think we can easily draw. Okay. We can easily draw. So let's say we draw this, or I think I have the picture. Okay. So this is the draw. So what you are trying to do here is first you need to set up the interval, and then the key part for this interval is the -1, right? If you see from this piecewise functions, let me erase this for a while to see it's more clear. You see that the -1 is playing important role both for the domain. Okay, so for the intervals. So we are going to look on our -1 here. Okay. And now we can start either way. So maybe x squared, if you think x squared is easy, you can set up just like a normal x squared. Maybe you can draw like a usual x squared here, but when you see this -1 here, you need to erase this part. Okay, and then you see that the domain is not include -1, so it's an open interval. So you can make this white circle here. It's open interval. Okay, and then from the domain less or equal -1, you see that it's 1 minus x. Okay, so 1 minus x, you can try to maybe for the very first time you are going to draw like a line like this, but then you see that it's -1, so you can erase the one that not needed. So you can erase that part, and remember that -1 is included in the interval for this one. So we are going to have a closed interval, so we can draw this full circle with blue color here. Okay, so that's how you draw the this piecewise defined functions. Okay, this is just a sampling with simple formulas, but the idea is still the same. Whenever you have a more um, maybe complicated function, but the idea is still the same, okay, for piecewise defined functions. Okay. Okay. From this piecewise defined functions, because we know that in one functions we can have several parts of formula. I mean, we can design by our own self for that part, for the equation itself. Uh, the other thing that is similar to this piecewise defined function is when we have absolute value. Okay, we can have absolute value, and we can break down the absolute value becomes at least two equations, okay, or two conditions. Okay, two conditions. So the next thing is the absolute value. Okay. So recall that the absolute value, we say that this is absolute value, by definitions is a distance from A, or maybe because it's A, but let me just write with x to make a difference. Distance is a distance from x to 0. Okay, that's the definition for absolute value. So absolute value is clearly just a distance. It's not really represent the numbers itself, but it's a distance. So every numbers that comes inside this absolute value, we need to make out the positive value out of it, okay, because it's a distance. On I forgot, on real number line or real line. Okay, so this will be always positive for every number x. Okay, so I think I will move this right things. Let me cut this and move to the next page to make it more clear. Okay. Okay. So if we have this symbols absolute value of x, okay, then we can have the inside. The inside can be negative and positive as well, right? Because both of them in the resulting in the end results will be a positive one. So we can say that this will be same x if x is positive, right? And this will be a negative if x is less than 0. Okay? So basically, we can make out our piecewise from this absolute value. That is, this is x and negative x. So this is if x and if x less 0. So from here, we can easily to draw the line, right? This is just a line, okay, just a line. So we can draw that. I think I have this. Oh no, I think we can just draw by ourselves. So just draw a line. The first line is just x. The other line is negative x. Okay. So we can say that this is our functions, or our curve absolute value of x. And the key is the domain is this 0. Okay, the one that has positive domain will be just y equal x. So this is y equal x. This is y equal negative x. Okay. So that's the absolute value. Okay. Okay. The next thing for this introductions, chapter 1 introduction is even and odd function. Okay, to give you some basic idea on what is this even and odd, maybe the easiest way to see is from maybe y equal x squared and y equal x cubed. Maybe this will be easier to see. Okay? What does it mean? So if we draw this y equal x squared, I think you'll see that the functions or the curve is basically, you can mirror through the y-axis, right? You can mirror. You can say that this is has a symmetry. It has a symmetry. While this other, maybe not really good proportion, but more or less, this is x cubed is something like this, right? We say that this is a symmetry, right? This is one way to see the visuals between the difference between even and odd functions. But there are more general terms that can be used to distinguish between even and odd functions. Okay. First is look on this x squared here. If we have 1, of course this is another 1, right? So when x is 1, y is 1. When x is 2, y is 4, right? From the x squared. Okay. Now let's look on the left. Okay. If we have -1, it's 1. If this is -2, it's the same 4. So when you put your negative, it becomes the original functions, right? Becomes the positive one. So we can say that for an even functions, if a function f satisfy f and then put -x, this will by the end results going to be the positive. Okay? For every number x in domain. So we call this even functions. Okay. So that's why when we have this x² is even function because let's say we have the x² like this, and then we put our -x in our functions, which means that we put -x and then squared. It's become our x². So that's why it's even function. Okay, it's going back to the f of x. So we get this is an even function. Okay. Now what's happening with odd functions? Now if we look the odd and just uh, from some trial and error from this x cube, you see that when you have the negative, it's still a negative. It doesn't going back. It doesn't going back to the original positive one. So it's still a negative. So when you have this odd, okay. So if f satisfies f, put -x, and then it's become negative of f of x for every number x in domain. Okay. So when we have the x cubed, we put -x inside. So -x, 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 it's negative x cubed, which means this is going back to the negative f of x. So we say that this is odd function. Okay. Now, from this definitions or from this method to find whether the function is odd or even, I hope if you are given a functions, you can tell the difference. You can tell whether it's even, whether it's an odd, or maybe not even and not odd. It can also be true. Okay. So even, odd, or neither, both of them. Okay, let me go to one last section before we have a break. I will take some break after some few minutes. Okay, maybe 5 to 6 minutes break. Okay, if you have any questions or maybe something to discuss, please write in the chat box. Okay. Okay, the last part for this introduction of chapter 1 is we call the increasing and decreasing functions. So as it's mentioned, increasing, decreasing, it's supposed to be easily to be distinguished from the words itself. Increasing means it's going to have some speed, and decreasing maybe going down like that. Okay, so let me just give you the graph. And you can see that if we make a segment, okay, if we make a segment from A, B, C, and D, we're going to see that from A to B, for most parts, is I think it's just an increasing functions, right? It's just increasing functions. It's here, it's increasing, and then from B to C, we see that it's going down, and from C to D, it's going up again. Okay, it's very easy to follow, right? So we can just say that increasing function is if, okay, fx1 is less than fx2 whenever x1 is less x2, and decreasing if is greater than fx2 whenever x1 plus x2. Okay, so x1 and x2 is just a sampling that you can put in any x that can be in the graph. Okay. So for example, if you take this, like for example, this point here as your x1 and this is x2, means that x1 fx1 is greater than fx2, means that it's decreasing. Okay. How do you know when a function is neither? Do you mean the even and odd, right? Okay, let me go back a little bit. So when you have even function, remember this is going to be your expected result, okay? And this also going to be expected result. So whenever you find any forms that is not negative f of x or f of x, maybe going to be the different functions, maybe going to be g of x or h of x that is not defined yet, then that is not even or odd. Okay, so that's how you define. Okay, so whenever you are having outside of these two forms, okay, it should be f of x or negative f of x. But if it's not both of them, then it's we cannot decide whether it's even or odd. Okay. Okay, I think increasing, decreasing, very easy to be understand, right? It's intuitively easy from the words itself. It's already describing what's happened to the functions, right? Okay, now I will take a break for maybe 7 minutes. Okay, 7 minutes break, and we can later continue uh, our class. So if you want to maybe drink or go to the toilet, okay, you can do so. Okay. Okay. Before we continue, I will try to do some practice, okay? Just to see whether you are get the point or not. Okay. Okay. Now, if we look here, there will be a tree curve that is going to be our concern, and we are going to determine whether this is a function or not. Okay. So the question will be determine whether the curve is function or not. If it is a function, find domain and range. Okay, you can try to, let me just write this is 1, 2, 3. Just in the chat box, this is an really easy samples. Okay, what's function? If it's the functions, what's the domain and range? Yes, second not of functions, 1 and 3 functions, okay. Okay, the first thing when you have the this tree curve, the first thing to decide whether it's a function or not is just to just draw a vertical line. Okay? D -2, -2, 2, -1, 2. Okay. Okay, really good. So first, we can just determine through this line like that. And the second curve, if you draw here, we can get 1, 2, 3. 3 sections that is crossing by this vertical line, so it's not a function. And the 3 is also, if we draw vertical line in every x, then I believe 1 and 3 is a function. Number 2 is not a function. I think you guys did very good job. Okay. Okay, very good, very good. And then we can decide the domain from just looking at the picture. So we see that this is -2 until 2, right? -2 until 2. So we can say domain, we can just write, and it's include inside, it's a closed interval, so we can just write, sorry. Yeah. And the range, we can just look the very bottom that is on the curve, it's around here, and the top is around here, and that's our range. So we are getting the -1 until 2. Okay. So this is not a functions. We not needed to write the domain or range, okay, because it's not a function. Number 3. So the domain, we could write the domain. That is, if we see that we take this -1, -2, -3 here, right? -3, and we are going to see this one is 2. So every x within this -3 and 2 will be our domain. So no domain will be, yeah, Christian, correct. Yeah, good. -3 to 2, but For range, it's not quite correct, your answer. So the range, remember, we have this missing link, right? We have this missing link. So what should we write here? So first thing, let me just write here, this is -3, right? So -3, and then up until this -2. So we write this first as our part of range. So -3, it's included, and -2, it's open interval. Okay, and then we need to add with this one, the -1, right? And then up until this part here, which is 3. Remember, not this one, okay? The very top, the very possible range, okay? So we are going to write that this is 1 to 3, okay? I think number 3, very challenging for writing this domain in range. Okay, I hope you get it for number 3, how to find the uh, range, okay? Oh, right. Good, Peter. Yeah, good, Peter. Yeah, sorry. I forgot the negative here. Should be negative. Yeah. Very good. Thank you for correcting my mistake. Okay, good. Uh, Let me check. Okay. The other part, some of the typical questions that can be uh, mostly will be coming. Okay, is finding out the domain of the functions. And I will give you at the summary what you need to at least emphasize on this finding domain questions. Okay, so this is finding domain through the curve, but if we just given in the description of the formula, uh, we need to also imagine what possible x that can be put through this formula. Okay, for example, okay, let me just go into the next page. Okay, I hope you finish this part. Okay, let's go to the next page here. So the question is to find the domain of the function. Okay, we can start with let's say we have irrational functions like this. Let me give you several questions at once, so you can decide which one you are going to work on. This part is, let's just say we have this. And maybe two questions first. Yeah, Peter. Okay, good. Yeah. Okay. So for number one, the first one is for every x that is not 3 or negative 3, right? Except 3 or negative 3. Okay, so let me just go through this first one here. So the rational functions, uh, I think I mentioned in the basic of math class, if I'm not mistaken. But let me just rephrase my definition here. That if you have this rational functions, the one thing that you need to be taken care of is the denominator here. Okay, because every time you have a rational functions, the bottom part of the functions should not be defined as 0. Okay, so you can write that uh, define this. We can write this define for all x except when x squared minus 9 is equal to 0. So this is, I think, definitions in the math world. Okay. So number 2 x. Yeah. Uh, the number is okay, but I think it's not complete for number 2. Okay. 5 and negative 1 is correct numbers, but you need to complete the answers. Okay, let me just go through the first one. Okay. So, oh yeah, correct. X greater 5, x less negative 1. Okay. But you should have, can it be equal or not? Because, oh yeah, okay. Yes, okay. Okay, good. Okay, very good. I think you're already really okay. Good foundation of math. Yeah. Yeah, it can be equal, right? Yeah. Okay, so from here we can just decide to factor out this x squared minus 9. Then we get that we have this x equal 3 and x equal negative 3, which means that this part is not going to be 0. Okay, so we can write the domain. We can write, you can choose how to write the domain. Okay, we can write the domain as like this. X is element of real numbers, as x is not equal 3 and x is not equal negative 3. This is okay. Or you can write with intervals. Okay, this is also, I think you need to keep in mind how to write notations. So first is we can write the whole thing like from negative infinity until some numbers that is not included, right? And then put the union, not u, sorry, it should be that like that. And then from negative 3 going to 3, right? And then put another union, and then 3, and then infinity. It's quite long, but it's okay. But if you think that just left notations, I think it's also okay. Not a problem. Okay. Okay, and then we have the square root. Okay, the square root. So first is rational functions. You can your concern is the bottom part, and then the square root. Your concern is the inside of the root, right? Inside of the root. Okay. The inside of the root. First, we need to decide what is root, right? What is this root? This root means that uh, if this is a real number, if this is we are in the real world, okay, not imaginary. If this is a real world, real numbers, then the one that should be inside is it start from 0 until all the positive numbers, right? All the positive number, or we can say that this should be, if this is a, and a should be greater or equal 0, and that is our restrictions. Okay, so this will be defined. Okay, so we can say define when the whole thing inside, we can write is greater equal 0. So we can just factorize one more time. Factorize negative 5 is x minus minus 5 or plus 1 and x minus 5. So we know that this will be, these two numbers will be an important number that restricted our interval of domain. Okay. So how do we know that our answer is correct? Okay. So first is we can decide by testing the numbers. Okay, testing the numbers between negative 1 and 5, or less than negative 1 and greater 5. But the easiest way to visualize or to represent the answer is just draw a line number. Put this negative 1, 5. Okay. And then we can testing the numbers in between or less or greater 5. Okay. So checking 0. Checking 0 is negative, right? Checking 0 is checking maybe here. So checking 0. 0 we put here, it will be a negative, right? It will be negative. So we write negative. Okay. We check, let's say the easiest number that we can think will be negative 2. Okay. Negative 2, put through. Yeah, let's just put through here negative 2. It's become negative 1. Negative 2 here is become negative something. We don't really care about what the number is, but it's negative, and negative will be a positive, right? So it's positive here. And then 5, we put through maybe 6. 6 plus 1 is positive. 6 minus 5, it's also positive. So it's positive. So this will be your answer. And since we define that it should be having some equal, so this will be a closed interval. Okay, I think real line number is easy to define. Yeah, we can just define this as like that, right? And then union, and then put through the 5, and then infinity, and then open interval. So this is the domain. Or if we would write in more delicate notations, we could write something like this, or x 5. Either way is correct, and you can just write with the first one here or the second one. It's correct. Okay? But the important thing here is to show you that the line number really can help. It really can help. Okay? So whenever you have like several x as like you have some inequality. Okay, so we say that this is inequality, right? This is inequality. This is just my tips for you. Okay? Whenever you find inequality, to give you more confirmation and clarification to make sure that this is correct, you can just turn to the line number. Just draw the line and then testing the numbers, and you will be fine. You'll be fine. Okay. Okay. I hope you get the idea. Okay. Okay. I think enough for practice. If we need more practice, we will have maybe tomorrow or maybe next week if we want to have some more. But I think it's okay. Uh, the basic idea is already given. Okay, well, zoom out. Oh, yeah, okay. Zoom out. Uh, Not sure how. I think this is okay, right? Okay. Okay, now what I would like to show you is some of the typical functions that uh, that might be comes around in our calculus courses this semester. Okay, so let me go through. Let me check whether I have. Oh yeah, I have. This is essential functions for our course. So first one is just a linear functions, just a line. I think it's easy to understand and not really any difficult things there. And then the second one is the power functions, or we can say polynomials, x squared, x cubed, x four, x five, and their variations. Okay, their variations. And then the root functions. Okay, now let's see the root functions. We erase the bottom part, right? Remember, because if we write completely like this, then it's not a function. Remember, is we have this vertical line, and we know that if we crossing more than once in that curve, then it's not a function. So we need to remove the other graph. Okay? And then for the cube, the square cube here, the cubic root, uh, we can have the negative one, right? We have the negative one because it's fine if we have the negative one, and we don't really need to erase because from the vertical line it's okay, right? From the vertical line it's okay. And then if we have this even root, we remove the other part. We have the odd root, we just draw as it is, right? Okay, so that's the root functions. And the other function that essential is the reciprocal. So 1 over x, 1 over x squared, and their variations. Okay. If we look here, we see that because of when we have x equals 0, that will be undefined. You will see that it will never reach the x equals 0. It will never reach the y-axis, right? It will never reach this y-axis here. And also the same thing happened here. Okay. So that's the 1 over x. 1 over x squared is the, if we put the x squared, then it will all be positive in y, right? And same thing if we have the cube and then the even reciprocal, okay? So reciprocal functions, we will learn more about this reciprocal and how we deal with it when we learn about limit. Okay. And then exponential and log, both are in characters. They are similar in the curve, right? Similar in the curve. Just you turn the curve. Okay. So the exponentials, if b is positive, and if b is less than 1. Okay. And this is for log. And you know that the log and the exponent, they are both inverse each other. We will talk about that later. Inverse and the exponential and log. Okay. And then the trigonometric. Okay. At least just 3 functions in trigonometric. It's enough to know. Okay. Sine, cosine, and tangent. Sine and cosine both are complementary each other because this co in cos, which means it's complementary. So it means it's complementary sign. Okay. So the basic one is the sine, and then it has a complementary curve or complementary equation for the sine. We call the cosine. Okay. What this complementary means, it's going to be, so basically your curve is the same thing. The difference is when you shift the angle. Okay. So you shift the angle about 90 degree. Okay. You'll see here, this is 90 degree here, right? This is 90 degrees. So you shift about this, and then we have the sine. Okay. And I think you have learned also in high school, and I will talk about it more in basic of math. How, if you want to know more, like the basic property of this trigonometry. And then the last one is the tangent. Okay, the tangent, because the tangent is going to be sine over cosine, and we know that sine and cosine, they have 0 in the results. So it's, by intuitions, we know that there will be some points that will have undefined conditions. Okay, for example, this one here is pi over 2, pi over 2. Because at pi over 2 and negative pi over 2, our cosine will be 0, which means that this part here will be 0. So that's why this will turns out to be having, we call the asymptote. We will talk about that later. Okay, so this is just to show you what kind of essential function that you need to know beforehand. Okay. 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 The next part is we can actually uh, change one function to another with some. So we can move, like for example, we have x squared. If you want to move up, move down to the left, to the right, we can do that. And we say that this is what it's called how to make a new function from the old functions. It's called the transformation of functions. So we start from the really simple, really simple. Before we learn another transformations that you will learn on in the next part of your courses. Okay. Okay, so new functions from old functions. Okay. So first is we need to understand the transformation of functions. Let's say f of x. So let me just give you illustrations. Okay. So if we have, let's say, just typical x squared. So let me decide this. And then let's say this is the same x squared. And we move this, maybe this is 2. So this is y equal f of x equal x squared. Let's say this is also, this is actually the same f of x. Okay. Okay, so we move this 1, 2, right? So we say that the new functions here, it's become the x squared plus 2, right? Okay. Now, if we have the uh, same curve x squared, but let me move the curve around here. Maybe that way, and maybe this is 4. Okay. How do you write this new functions? Let's say we are not using this x here. Just let's say this is f of x. Okay, it's f of x. So what should we write here? Let's just write with f of x. X squared minus 2x. Okay. Okay, so if the first one, okay, if the first one, let's say if this is just f of x, the first one is just plus 2, right? The new one, the new functions. Now the second one here, the third one here, this will be y equal f. Now it become x minus 4. Yeah, correct, Renato. Yeah. Or in our case, this will be x minus 4 and then squared. Okay. Now let me just make some conclusions here to see whether this is okay. Oh, sorry, not this one. Which one? Oh, this one. Now this is how it looks like. Okay. Okay. Now, whenever the f of x is going vertical, or it's shifted through y-axis, we are just adding with the units that we are moving. If we are moving in a positive way, we need to plus with the units. Okay, so we take this and plus c. Okay, if we are moving downwards with some c units, then we say that we are going to minus that functions. Okay, fx minus c. Okay, the middle one is the original functions. Okay. Now, if we move to the right and the left, it's a little bit counterintuitive if you think when you move to the positive, you think that, oh, you need to plus. But remember, the horizontal is the x-axis. Okay? So it's different when you say that f of x plus, it's different. It's the x-axis. So what we are going to plus or minus is the x itself inside the function. Okay? Now, when we look at the x-axis, we are going to have, when we move to the right, we will have the x minus c. And when we move to the left, we will have x plus c. Okay? Now, how to make this proven or useful for you. Right? We can just start with a simple, if you want to start with just f of x is equal x, okay? Just as simple as that. Okay. Or maybe x squared, maybe it will have a more reasonable answers. Okay. So if we take fx, let's say minus 1. So we have x minus 1 squared. So we have x squared minus 2x, right, plus 1. And then we know that this will, where does this going to have the roots? It's going to have the roots at x equal 1. The vertex is 1, right, as x equal 1. So 1 here, maybe 1 is here. So it's going to be like this, right? Right? If you have the x squared, maybe x squared is this, right? Is it going to the right or left? It's going to the right, right? Okay. So that's how you see whether this is speaks the truth or not. Okay? We can just take some time to see how the function shifted. Okay. Okay. Is it clear? I think it's clear, right? So you shift it. If you shift the within the vertical axis, the y-axis, then you will have just plus or minus according to your units that's going to be shifted. And when you shift it horizontally, then you need to plus minus the inside of the functions. But when you go to the right, it means that x minus something that you are going to shift, okay? Some units that you are going to shift. Okay? I hope that's clear. Okay, you can just try for some. I think you can try for most of the functions that you will shift it. But my suggestion is just try some simple function that can be easily compute. Right? Another way for the transformations that I think I will also explain more later, but I will just show you the graphs here to give you some idea. I think we can make it a little bit smaller. And then going to put them here. Now another way or another transformation that can be done easily and visually can be understand is first is we can stretch our curve. So the original curve is this black curve here, f of x. If we multiply with some constant, okay, and the constant is greater than 1, so 2, 3, 4, 5, and so on and so forth, or maybe 3 over 2, 5 over 2 is also greater than 1, then you will stretching your curve vertically. So you will turn your curve like this. Okay. You can check also with the x squared, and when you multiply with this, what will happen? Well, you can try to draw this, or you can just open your GeoGebra, go to the website GeoGebra, as I show you at the beginning of the course in the Monday session. You can try to go to the GeoGebra, plug in the curve, and see what's happened. Okay. And then if we multiply with 1 over the constant, so which means maybe 1 over 2, 1 over 3, 4, and so on, we will stretch the curve horizontally. So it's like you have a rubber. You stretch vertically, you stretch horizontally. Okay. And then last thing on this transformation is if we reflecting or mirroring. So the original function, if we want to mirror through the x-axis, we need to multiply with -1. Okay. You can also check with some simple functions, and then you multiply with -1. What's happening? Okay, and that's how you get the reflecting transformations. Okay. If you want to mirror through the y-axis, and now y-axis, mirror through the y-axis, you need to multiply with the negative the inside of the function, which is the x. Okay, this one. Okay, so it's going to be mirroring to that. Okay. Okay, that's the transformations. Okay, transformations. I think I will stop for today. Um, we will continue tomorrow. Uh, yeah, we will continue tomorrow for some part of uh, exponential. Um, yeah, and then log and inverse, and then that will be uh, completed for chapter 1, and we will continue with the introduction of limit. Okay, so hopefully tomorrow we can finish the chapter 1, and we can move to the introduction of limit. Okay, so any questions? Any questions? For the first part here, I'm trying my best to also um, make some additional points in the basic of math. Okay, because some part of this is actually the same as the basic of math. Okay. Okay, any questions? If there's no questions, then we'll stop until here. We will see you tomorrow, and we will see you in the classroom, right? The classroom tomorrow. Okay. Okay, see you tomorrow.